Hey, we're going to fiddle with some Goldbach again. I've made various, I call them tables or Excel spreadsheets, and they seem to be fun. I have read various number theory books, and for some reason they don't do these. Maybe it's original, maybe I'm, just figured out these things. I like tables, and it's possible that no one's ever thought of doing Goldberg with these tables. Here's one. I think this one isn't on Vixra yet. If they still want to keep, publishing me, this little one here is. All right, so you. I don't know why that's. There we go. You make a table going up to any number here, bringing the same number up here, and then counting up to 20, and all of the pairs in another document that maybe we'll get into. I try to formalize these ideas in a PPT, I believe I called it a prime pair table. Right, so the idea is you do a sieve. Some of you who eat spaghetti know what I'm talking about here. You get all the water to drain out, and here we get all the composites to drain out, so to speak. So some are trivial, like one. I don't know if it's necessary to put it in there, but I'm kind of superstitious at this point. So the trivial ones, 0 and 20 you can do, and this one. And then the easier ones are after the first instance of, let's say, 2, you circle that and you're not going to remove that, but all of the subsequent evens you're going to remove from the top and the bottom. All right, and that's typical Aristophanes, a Greek philosopher, I think, or mathematician, came up with this idea. 3 is the next number that occurs as you kind of do this algorithmic design, moving from left to right. You keep 3, and then all of the multiples of 3, 6, 9, 12, 15, 18, you remove. Go to 4, you've already removed 4. 5 is not removed, and it's the first instance, so I've circled those things. And then all the fifth ones you remove. And I claim, and I don't know if you can give a proof, but all of the pairs that remain are prime pairs, where the pairs that remain have no slash on the top and no slash on the bottom row. So we get 17 and 3 and 13 and 7, and those add to 20, and they're prime pairs. Okay, so I don't know, what does that mean? Is that a solution to Goldbach? Does it always work? That's the catch with Goldbach is, it's pretty, it's fast. I don't know, is that fun? I guess that was fun. And but can I say it always works with certainty? How would I prove that it always works? It certainly looks like it always works. What it boils down to is where you get these remaining primes. You could say, in another idea, a binary prime pair table. Instead of slashing them out, you make all of the ones that survive a 1 and all the ones that fail a 0. And so then it becomes what is it the case that for all of these tables you have 1s in the same call them a cell, a Goldbach cell, GC, in this more formalized document here. try to define such things and develop it a little bit further. I guess I'll attempt to post this at some point. Fixer might be getting annoyed with all my drafts, but anyway, once you do, is that always going to be the case that you'll get a 1-1 after you do this routine? It's possible you could get a, that's a prime, it has a 1, and this is a 0 down here, and you systematically, screw the algorithm, there's none that survive with a 1-1. The kind of rub with that is that the density of 1s in the lower row is quite, a lot, because I'm not removing the 3, whereas I'm removing all the 3 multiples up here. I'm not removing the 5, but I'm removing all the 5 multiples up here. So I get a pretty good stretch with nothing but 1s. And up here, the 0s are getting more numerous. So you're pulled two ways. I can see that it might be true and it might not be true. This is, as I say, kind of dense in the 1s, and this is kind of getting dense in the 0s. So do they always marry up? That seems to be the central thing lacking in a simple diagram like this. I tried a more elaborate diagram where you can predict the primes where they occur. And that's by way of doing a module. You call it the modular table, modular prime pair table. You have a repetition of the table down here. Here I'm starting at 0 and I go up to 26. And as I go along, I change the idea. I put primes down here, 2, 3, 5, 7. Start at 0 as usual, 1 and then 2. And then with the prime of 2, I'm alternating. I can do this very fast, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. As I say, it's a binary idea for that one for sure. And 0, 1, 2, 0, 1, 2. Eventually you replace the greater than 1s with 1, to make a real binary primary pair table. So here's the idea. Wherever you have a non-zero above for the first time, you make that a new prime. So for 3, I have a 2 that's the only one in contention. I'm going to make that a prime. And I keep on going here, and when I hit 5 right here, I have 2 non-zeros. That becomes another prime given by an S here for, stay or stable or something like that. Here I'm eliminating at 6 via zeros at 2 and 3. So this one is out as a potential Goldbach cell. The next one, I get a string of non-zeros, and that becomes 7, a new prime. I leave that one in with an S. The next one is zapped with a 2, next one with a 3, this one with 2 and 5. Next one is 11. I have a string here. Notice I'm just have 2 through 7 primes. And this is kind of interesting. You get a lot of tables with just 2 primes with 1 prime, and we'll explore that in a second. So the point of this thing is I can now, without knowing ahead of time, see the solutions as having all non-zeros in these rows here and all non-zeros in these rows here. This 7, that 0 doesn't count because this is this S, a stable, first one, whatever. And this is grayed in, and that would be a Goldbach cell, as I've been calling them. And you get one down here as n, and 2n is a prime, and the sum of two primes works automatically, and you're done. So you might be getting some ability. I've never explored in any book that I've ever read that you can get these prime factor, so you had a name for it, prime base depictions of numbers, where you take this a little bit further and you get the remainder when C is divided by P is X and the quotient is Z. And then you stack these up for all primes from 0 to 2n, and you string them along. That would seem, I strike my representation, to be a unique representation. Between those three, you're getting quite a bit. The number, its remainder, and its quotient. So can you, given that those things are present in a table like this, can you predict that if this is a prime, the 3 is a prime, and then when I loop around, that will be a prime there in this position. Therefore, I'll have a Goldbach cell. Same with this. I'm looping around. I know by calculation on these things in the periodicity of these two, sort of like, let me break here and express a few things, sort of like a Fourier series or music idea where you have various waves now at the same time, additive. I guess they don't have to be additive. They can exist at the same time. And I think with these primes, you have them, go up and go down, I guess, or they just bang back into the x-axis, go up, bang back into the x-axis when the remainder is 0. So actually it'd be they spike up and then they slash down, so 0, 1, 2, 0, 0, 1, 2, 0, 0, 1, 2, 3, 4, 0, 0, 1, 2, 3, 0, 1, 2, 3, 4, 0, 0, 1, 2, 3, 4, 0. So will these predictably have troughs, fancy word, or places where they're all non-zero? They're all above the x-axis, and then you can predict when the next prime is. I don't think they've ever done that. It doesn't sound particularly easy to do that, but that would be, and you could see how you also have, per this idea, this I published in a paper on Vixra, that the catch is when you hit all non-zeros, mod non-zeros for whatever primes you currently have, you add another prime, you add another wave, and you start it at 0. Right? So it's additive, and it would seem that if you could, how you add dynamically as you're going another function to a series, sounds pretty reasonable. And you could, backtrack it where if you add 17, for example, when you hit it, starts at 0, and then you go back from 17 so that it is going up to 16 and spikes down to 0. You have the remainders with a quotient of 0 of 17, and then it continues. And that kind of thing, I know this is getting a little wild. That kind of thing I also made a, table for, and that one looks like this. where you start, 1, okay, 1, 2. Those are two non-zeros, so I'm going to add a 3. And that counts as a prime. And I back log with remainders of, actually it's 4, I'm including 4 in this thing, and I keep on going. It's a kind of a simplistic table, kind of a strange table in a way. You fill in the 0 1s as I was doing before, and then the 2, 1 2 0 1 2 0 1 2 0. Those are the remainders. I'm not getting the quotients on these. I'd have to count them up. And it's hard to get superscripts in Excel. And then you go to 4, and you continue with this thing, and you make a table, and you start to notice that you get a pairing with center 0. There, it seems to always exist a prime at minus 1 2 3, namely 7, and a prime at plus 1 2 3, namely 13 over here. So it seems like you're pairing. And the problem with Goldbach is you get so many solutions. You just want one solution for sure. And this seems to be of that type where we have one solution. I guess it'd have to be unique. The nearest symmetric pair of primes from a center. Is that always the case? That would, I think, get the logic of Goldbach. It's very easy to get confused with. You see all these cases, like all these tables, and it seems to be working great. But do you have a proof? I think that would be a proof for every. Let me see how this would go. For every Goldbach table, these are essentially tables. You have a 0, and you count up. Starting at the high on the spreadsheet, row 1, and it's going down, and then with the prime pair table, you make a curve and go back up. With this, you keep on going straight down. But nonetheless, they pair up in the primary pair table, and here they're symmetrical, so you can go from this to a primary pair table. And if you could use this to prove that a primary pair always exists, then they exist in the tables. And I think that does it. Seems like an induction proof. You could do an induction proof. All the tables prior to one work. Does the next one work as well? And I have some idea that you reverse engineer it. You have a table that works, and then you reverse engineer it, and you get the two numbers, slide them away from each other. They no longer work, but I'd have to go, I guess, this way. But then you fill in all the rest, and you'll get a new table. And I guess you could infer that here's the catch again, always get a primary pair when you do that, question mark. This one is very suggestive that, you always get this, and it would seem like somehow I can do an induction. And there are some hints that if you've got all of these pure repetitions, no zeros, per force of your backtracking and filling in the new primes you're getting, the new numbers, You fill them all in. Back here, there's no zeros. Now, when you get over here, you get zeros and columns on the other side of this diagonal. So you're not removing any primes when you do this. Now, when you come down here, you're removing primes. So, for example, this one at 23 here, 23, I would remove with a 0 down here, not the first 0, but the second 0, the quotient of 2, I would remove all the primes that occur back here. Currently they're not being impacted. They're not impacted until, 23 from now, from this position. So the primes remain intact, both for here and up until that point. Is there a prime pair in between those two? So you have a limited, domain to look at. Also, you're limited by, you just run out up here. How could you establish that? You can make a Excel table where you have numbers, and you subtract from a list a certain amount. 1 minus 1 minus 2 minus 3 minus 4 minus 5 minus 6 from these numbers. You generate one table, and then you do a minus over here, the same table, and then you do the sum over here. And you'll get rows with the evens, all evens, and in each row, back in these 2 rows, you'll find a symmetric pair of primes. So another table, it seems close, so far, and yet so close and yet so far. Okay, so the other idea is to see if there's anything that can be said for just algorithmically proceeding. Does that count as a proof or an induction if you start with a table, you have various parameters for these primary pair tables, PPTs. You can look at a single prime with the 2n, 0 through n, up, another n through 2n. And with a p down here, 0, 1, 2, 3, 4, dot, 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 p minus 1, p with a circle around it, you keep it, and then you continue doing that. Okay, and then you're filtering for 1 prime, where you're getting a bunch of 1s. When you do the binary idea, you're getting a bunch, you're just removing a few. So I try to prove that you're always going to get 1s with that situation for some 2n's. Notice if you make the 2n too small, the p overwhelms it, and you get all remainders, non-zero after the start. And if p is small, then if it's big enough, it goes to makes it to the second line, and it seems like obviously you're going to get some 1s there. But if p is less than n, it's these short little things towards the end. If you choose p as in 2p, then they perfectly line up, and you're guaranteed to have some 1s. So the case is, the puzzling case is when p is not the 2n, it's not 2p, p is smaller than n, it wraps around, and do you generate 1s in that case for just p? And if that's true, if you can show that scenario for, I guess that'd be general 2n with those constraints mentioned, as well as general P with the constraints mentioned, then given that when you make these tables, you're always removing solutions, you have the 2 solution with a 2n, and you're getting lots of 1 pairs, and then you add 3 and you take those out, and then you add 5 and you take more out. So what remains would, I think, be primary pairs. Does that establish a proof? I'm starting to think that one might work. A iteration through a bunch of tables, bunch of combinations of parameters, and it seems exhaustive and to always work. Therefore, it always works. Doesn't seem to be quite as solid as I'd like. You'd like a document like this where you define a bunch of things, and eventually you don't have tables to ponder, but equations to see proved. All right, so that's what I've been up to. I'm going to attempt to make a bunch of these tables and see if I can iteratively get to a proof that's satisfactory to me. All right. The other thing is, I think it's getting very warm in Europe. Just mention that. No need to worry. We can always take care of it in the future sometime.